Hello everyone and welcome back to the class. Today in the course of circuit analysis, we will study a new passive element known as capacitor. A capacitor is a passive element which is designed to store energy in its electric field. Besides resistor, capacitors are also most commonly used electrical component, and these are extensively used in electronics, communication devices, computers and power system. For example, they are commonly used in tuning circuits, of radio receivers, and as dynamic memory elements in computer systems. A capacitor is a passive element which is designed to store energy and do not dissipate energy. This stored energy can be used later. For this reason, capacitors are also known as storage element. The application of resistive circuits are limited, but the combination of resistor and capacitor make another class of widely used components. And also, the circuit analysis technique which was studied earlier are also applicable to capacitors. The structure of a typical capacitor is shown in the figure 1. A capacitor consists of two conducting plates which are separated by an insulator or a dielectric. In many practical applications, the plates of aluminum foil are used where the dielectric may be of air, ceramic, paper, or mica. A capacitor connected to a voltage source is shown in the figure 2. When the circuit is closed, the source deposits positive charge Q on one plate and negative charge minus Q on other plate. And with this, charges are stored in a capacitor. And the amount of charge stored on a capacitor is directly proportional to the applied voltage. And mathematically, charge deposit Q is equal to CV, where V is the applied voltage and C is the capacitance of the capacitor. And in this relation, capacitance of capacitor is also constant of proportionality. Now the capacitance of capacitor is defined as capacitance is the ratio of charge stored on one plate of capacitor to the voltage difference between the two plates. Mathematically, capacitance is equal to charge stored divided by applied voltage to the capacitor. The unit of capacitance is farad, and 1 farad is equal to 1 coulomb per 1 volt. Now capacitance of capacitor is the ratio of charge per plate to the applied voltage. As it is a property of material, so it doesn't depend on charge or applied voltage, where it depends on the physical dimension of a capacitor. Usually, capacitance is equal to the product of permittivity of dielectric material between the plates multiplied by surface area of each plate whole divided by distance between the plate. And the mathematical form is shown here. Epsilon is the permittivity of dielectric material between the plates. A is the surface area of each plate, where d is the distance between the plates. Now from the given relation for capacitance of capacitor, we may infer in general three factors affect the value of capacitance of capacitor. The first one is the surface area of plates. The larger the area, the greater will be capacitance of capacitor. Now, second one is the spacing between the plates. Reducing the distance between the plates will increase the capacitance. And the last is permittivity of material. Higher the permittivity, the greater will be capacitance. Capacitors are commercially available in different values and types. And normally the value of capacitor ranges from picofarad to microfarad. Well, this is the range of capacitor most widely used or available. And the capacitor is well described by dielectric material, and from what kind of material they are made of, and whether they are of fixed type or of variable type. Figure 3 shows the circuit symbol used for fixed or variable type capacitor. Figure 3a represents a fixed type capacitor, where a figure B represents a variable type capacitor. Now according to positive sign convention, if voltage and current either both are positive or both are negative, the capacitor is being charged. And if product of voltage or current is negative, then the capacitor is discharging. The figure 4 represents various types of fixed capacitor which are commonly used. Figure A is a polyester capacitor, B is a film capacitor, and C is an electrolytic capacitor which produce high capacitance. Figure 5 represents most common types of variable capacitor. Variable capacitors are used in allowing one to tune to various stations in the area of radio communication, and in addition to this, capacitors are also used to block DC, pass AC, phase shift, to store energy, start motors, and suppress noise. Now we will find out current voltage relation for a capacitor. As we know that charge stored across a capacitor is the product of capacitance of capacitor and voltage applied to the capacitor. Now taking derivative of both sides for this relation, we will have rate of change of charge will be equal to capacitance of capacitor multiplied by rate of change of voltage. And we know that current is equal to rate of change of charge. Now substituting rate of change of charge by current, we will have current voltage relation for a capacitor. And here positive sign convention is used. The capacitor that satisfy equation A are said to be linear, and graphically is represented in figure 6, which represents a line with a constant slope equals to capacitance of capacitor, where the current voltage graph for a nonlinear capacitor is not a straight line. Although some of the capacitors are nonlinear, but most of them are linear. Now according to equation A, for a capacitor to carry current, its voltage must vary with time, and for constant voltage, the current flowing through the capacitor will be 0, and current is 0 ampere for open circuit. Hence, the capacitor acts as open circuit for DC voltages. Now the voltage current relation for a capacitor can be obtained by integrating the both sides of equation A, and will result in relation that voltage across capacitor will be equal to 1 over capacitance of capacitor multiplied by integral of current through the capacitor, or 1 over capacitance integrating current from start time to present time and initial value of voltage across a capacitor. Here V of t naught equals voltage across a capacitor at time equals t naught. Now equation B shows capacitor voltage depend on the past value of capacitor, which means that a capacitor has memory, where the instantaneous power delivered to the capacitor is equal to product of voltage applied and current passing through the capacitor, or capacitance of capacitor multiplied by voltage applied and product of rate of change of voltage. Now the energy stored in a capacitor is obtained by integrating the power of capacitor, where power of capacitor is a product of capacitance of capacitor, voltage applied to the capacitor, and rate of change of voltage. So it will equal to capacitance of capacitor product with voltage applied to the capacitor and rate of change of voltage. So cancelling out and changing the limits, energy stored will be equal to capacitance in product with integral with limit of voltage at minus infinity to voltage at present time V of t V dV, and will be equal to half CV square with limits given here. As we know that V of minus infinity equals 0 because we are assuming that capacitor was uncharged at start. So energy stored will be equal to half CV square, or substituting the value of voltage, the energy stored in a capacitor will be equal to charge square divided by 2 times capacitance of capacitor, where the equation C represents energy stored in electric field that exists between the plates of a capacitor, and this energy can be reused since ideal capacitor don't dissipate energy. In fact, the word capacitor is derived from element's capacity to store energy in its electric field. Now we should note down the following important properties of a capacitor. First property is that a capacitor acts as an open circuit to DC source. From equation A, when a voltage across a capacitor is not changing with time, that is DC voltage, the current through capacitor is zero. However, if a battery, which represents DC voltage, is connected across a capacitor, the capacitor charges. Second is, the voltage on a capacitor cannot change abruptly. The voltage on the capacitor must be continuous, and the capacitor resists an abrupt change in the voltage across it. Now, according to equation A discontinuous change in voltage requires infinite current, which is physically impossible. For example, the voltage across a capacitor may take the form shown in the figure 7a, which represents instantaneous changes, where practically it's not possible for a capacitor voltage to take the form shown in the figure 7b, because the capacitor will resist the sudden changes. Conversely, the current through capacitor change instantaneously. Third property is that an ideal capacitor doesn't dissipate energy. It takes power from the circuit and stores energy in the form of its field, and returns the previously stored energy when delivering power to the circuit. The fourth property is a real non-ideal capacitor has a parallel model of a leakage resistance as shown in the figure 8. The leakage resistance may be as high as up to 100 mega ohms and can be neglected for most practical application. For this reason, we assume ideal capacitors. Now, in the given example, you have to calculate charge stored on a 3 picofarad capacitor when a voltage of 20 volt is applied across it. Also find the energy stored in the capacitor. Now, starting the solution, we know that charge stored on a capacitor is a product of capacitance of capacitor and voltage across it. So Q is equal to CV. Substituting the values, we will have a charge of 60 picocoulombs. Now for second part, we have to calculate the energy stored, which is equal to half CV square. Again substituting the values, we will have energy of 600 picojoules. Now in the next example, we have to find voltage across a 2 microfarad capacitor if current flowing through capacitor is given by 6 product with exponential power minus 3000 t milliampere. Also assume that initial voltage stored on a capacitor is 0. Now using the voltage current relation and substituting the values of capacitance of capacitor and current and then integrating from 0 to present time t, the voltage will be equal to negative exponential with a power of minus 3000 t with limits which will vary from 0 to present time t. Substituting these limits, we will have a voltage of 1 minus exponential power minus 3000 t volts. And thanks for watching this video.